Okay, today we're going to be doing energy diagrams and relating them to reaction mechanisms. So as we see here, we have a three-step reaction mechanism, and we're going to be looking how does this reaction mechanism relate to this energy diagram right here. So we see that this energy diagram right here has three activation energies. This first one, and this second one, and this third one right here. Now, the first one is the slowest one. Okay, and this is our rate determining step. So this is our rate determining step, and it's our first one. And the reason why it's the slowest one is because it requires the highest potential energy for it to overcome. So it requires a potential energy that is this high. Now this one over here only requires a potential energy that's about this high, and the third step only requires a potential energy that's about this high. So the first step is our rate determining step, and that's why it is our slowest step. Now, as we remember from before, activation complex is the top of each of the activation energies. So the activation complexes are right here, here, and here. Now, our reaction intermediates are the products that are made in the middle steps right here. So our first reaction intermediate is, well, let's kind of skip ahead just a little bit. Here's our reaction intermediates right here at these valleys right here. So we have two reaction intermediates, and we have up here is our activation complex. Now, rate determining step, of course, is our first step, and we need to determine what are reaction intermediates. So as we see here, in the first step we make HOOBr, and in the second step we use HOOBr in the second step, so it's used up as one of the reactants. So this side, when we make our net formula, these things are going to cancel. Okay, and same with these ones. In our second step we make two HOBRs, and in the third step we use up those two HOBRs. Okay, so these are our reaction intermediates. So our reaction intermediates are HOOBr and HOBr. Those are reaction intermediates. And then what we can do is combine the rest and make our net reaction. So our net reaction is, we have HBr plus O2 and plus another HBr plus another two HBrs. So we have 1, 2, 3, 4 HBr plus an oxygen, and that makes, now this is not used anymore because it's a product here, but it's reused over here, and so it's on both sides of the arrow, so it cancels out. And same with this one. But 4 HBr plus O2 makes 2 H2O and 2 Br2. And it should be already balanced here. Just to make sure, we have 4 Br here, 4 here, 4 hydrogens, and 2 oxygens on both sides. Okay, and that is how we can relate a reaction mechanism to an energy diagram. Now, we don't have any catalysts here, because as we see here, these ones kind of cancel out here and here. Now in the last lesson we learned that if something cancels out going in this direction like this, then we're going to call that a catalyst, because it starts off in the reactants up here and is reformed in the products down here. Okay, and that would be the definition of a catalyst. Now we're going to look at the effects of a catalyst on activation energy. So as remember, a catalyst lowers the activation energy by providing a reaction mechanism. So here is an example of a reaction, and here is the amount of energy required for a reaction if it's uncatalyzed. So our activation energy for the forward reaction is this right here. So if we drew like maybe a little hash line, this would be our activation energy for the forward reaction. Okay, and if we continue on with this little line right here, this line way up here would be our activation energy for the reverse reaction. So when this reaction is going forward, it requires this much energy a minimum of this much energy in order for it to become products. And in the reverse reaction, it requires this much energy in order for it to proceed. Okay, so this is the activation energy for the forward reaction and the activation energy for the reverse reaction. Now we're going to look at the activation energy of the forward reaction when it is catalyzed. So here we have a two-step reaction, okay, because we have two peaks right here, and we can clearly see that the second peak is higher than the first peak. So this is the rate determining step. So we're going to make this this is the rate determining step, and so we're going to calculate our activation energy using this second step right here. So this second step right here, we're going to try to draw in blue, and this is our activation energy in the forward direction. Now again, if we take this and we extended this line, this would be right here. Now it's getting a little bit messy. This right here is our activation energy. So if we have way down here and we want to go into this direction, in the reverse direction, we have to have enough energy to overcome this determining step, this rate determining step, and this would be our activation in the reverse direction right here. Okay, and a little review of what our change in enthalpy is, well, this is our change in enthalpy. It is the difference between products and reactants. So in the forward direction right here, we see that it's a exothermic reaction, so it goes down, and therefore it's going to have a negative change. Okay, so delta H will be a negative number. Okay.